Hello, hello everyone. Well, thank you very much for attending. For the people in person, our estimated ESRs, and also the STEAM also audience that we have online. Thank you very much for sharing your time with us. And Roberto, Monaco, and I, we would like to present to all of you in person and online our tutorial on the use of system dynamics in energy digitalization. We will talk about enhancing decision making and also about regulatory analysis. And we will specifically dive into the distribution grids domain of the energy sector. Perfect. So just as a brief recap, during this week, we're having the summer school of the InnoCyPES project. And within the InnoCyPES project, we are a set of 15 ESR, what we call ESRs as early stage researchers, and we carry out research in multiple topics, from oil and gas to distribution grids, passing through transmission grid, generation, and all these topics go across multiple disciplines and also are organized in different work packages. But today, after the presentations that our colleagues gave into offshore wind control, robust control, or for instance, communications in offshore wind power plants, we would like to focus on the economics and social part. This were ESR 14 and 15, which in our case is Roberto, Monaco, and I. We would like to give an overview on what's the value of all these digital technologies, on how to assess them, and also how to evaluate the regulatory barriers that are arising across this deployment of digitalization. So about the presenters, just a little bit. So, well, Roberto, Monaco, and I are enrolled as Ph.D. Candidates at the DTU, Roberto at the Department of DTU Management and Industrial Economics. And in my case, at the Department of DTU Wind, we both are third-year PhDs. It's been already a long travel, a long journey with many secondments across Australia, Canada, and different other places with whom we have shared very good moments and very good learnings as well. And we have also recently joined the United Nations, the European part of the United Nations Economic Commission for Europe, as collaborating with the expert group, the Task Force on Digitalization in Energy. And we would be more than glad to give this presentation today, complementing and showing more about the topics we are addressing from day to day. This is just an overview of the collaboration network that we have been working on across Australia, Canada, Europe, DTU also in collaboration with EDF and Adina, our colleague also ESRs, and other ESRs. And basically for today's presentation, I just want to answer two questions first before starting, maybe just to attract a little bit of attention also on the audience in terms of who is this tutorial targeted to. So people that is attending online or in person is not lost in saying, why I'm attending this tutorial. So basically, this tutorial is focusing, it should be showing some bubbles here, but basically the idea is that the tutorial is targeted to energy professionals. So we try to address and give a basic knowledge on the matter on in this case, system dynamics, which is a methodology we will talk a lot about. And but specifically, we target also professionals related to electric utilities, national regulatory authorities, but also system dynamic modelers and power system analysis experts as well, because it's another type of modeling tool we are addressing here. And what are the topics? I already anticipated a little bit. We have a socio-techno-economic focus, assessing the cost and benefits from a financial perspective and also from a societal perspective. A regulatory focus, especially Roberto, addressing how the regulation can foster more digitalization and address the barriers that exist nowadays, and on system dynamics, which is our core keyword or set of keywords, and then the main methodology we will address here. So after this very quick introduction, I would like to just outline the agenda for today. So I already anticipated the first points, point 0 and point 1, which also with 2 and 3 belong to the main introduction of this presentation. So Point two is where now my colleague Roberto, I will give the floor to Roberto, where he will introduce what are the challenges nowadays in distribution grids, digitalization, and how this links and demands for more specific modeling tools to better understand the distribution grid and better understand why digital technologies can make an impact and why can we address the different barriers that we are facing for the deployment. Afterwards, I will give the basic knowledge. I will introduce to all of you and also the audience, the online audience, the basic of system dynamics, the foundations, core concepts, core elements, with some examples that I hope are as more instructive as possible. Then we will have a break for our colleagues to have very nice coffee that we have here in person and also online to take a coffee. And Roberto will take the second part with a first tutorial on qualitative analysis, how to use system dynamics from a qualitative perspective to understand better the barriers of the deployment of digitalization in the energy sector, specifically to distribution grids. Some break, and then I will take the next part, addressing the quantitative part, how to build a quantitative model from scratch with system dynamics, and how I did it with my Ph.D. and with a more advanced application. And we showed that, in this case, I'm anticipating that it's in the Portuguese context, that we managed to make a large scale model or business model replica of distribution grids, and we assess different policies. So without more delay, I will give the floor to Roberto to start his first introduction. Thank you very much.
Thanks. Thanks a lot, Jose, for this very nice introduction, comprehensive introduction. And once again, good morning to everyone. It's super nice to have you here to follow this tutorial on system dynamics in energy digitalization. And once again, I really would like to thank you, all the online participants that are here with us today. As Jose already mentioned, today we are going to talk a lot about digitalization, in particular, digitalization investment in power distribution grids. So what I'm going to do now is to with you, try to understand why today we are talking about digitalization. So why digitalization is a key enabler for the energy transition. Then also trying to understand why we decided to focus on distribution system operators. So why DSOs are going to play a pivotal role during this energy transition, and also how we end up to use system dynamic to face the barriers that we encounter during our research. So let's start to think about why we are talking about digitalization. So as we all know, climate change has prompted us to reconsider the way we consume and we produce our energy. And this motivation why a lot of new ambitions decarbonization target has been set worldwide. And in NewPol, for example, we have a lot of strategic policies that have been applied and implemented, like the European Green Deal, the Repower for EU, and also the Fit for 55 package. And all this strategy policy has an aspect in common, and then the mission to decarbonize our energy systems. However, the decarbonization of our energy systems is changing the energy sector as we used to know it. In particular, following two main trends, the trends of the electrification and decentralization. Because when we are talking about decarbonization, we think about investment in renewable energy sources and distributed energy resources. So this is causing, of course, a decentralization of the energy production and also on the energy management. So that's why we're talking about decentralization. And also, when we think about the electrification, we think of increasing investment in the electrification of the heating sector, but also electric vehicles. And of course, these two main trends are causing an increasing complexity of the management of the energy system, which require more flexibility. And of course, in order to unlock flexibility with the real-time operation and management, and in order to unlock this potential, then we need an enabling tool, and this enabling tool is digitalization. So that's why digitalization is a key enabler for the decarbonization and so the energy transition. And now, this is just to understand why we decided to focus on distribution system operators. So this is the configuration, the conceptualization of electricity supply chain as we currently know it. And of course, there is a unidirectional energy flow that starts from the generation of big power plants then is transmitted high voltage and distributed low voltage with distribution system operators to the final customers. However, with this energy transformation, this is the new configuration of our electricity supply chain. And as you can see, there is a lot of changes, especially at distribution level. You see a lot of new actors that are emerging at the interfaces between the distribution system operators and the final customer. We have emerging actors like aggregators, prosumers, and also an increasing integration of renewable energy sources, smart meters, and smart chargers for EV vehicles. And of course, this was one of the motivations that make us to choose distribution system operators as our main target, as they are going to face a lot of challenges. And in particular, when we are talking about renewable energy resources, the 70% of the capacity of new renewable energy resources in the EU and UK will be connected to the distribution grids. And the distribution system operators, from one side, are facing a lot of challenges in integrating new renewable energy sources, EV, so they need to increase the capacity of the grid, a grid which is old and where the observability is still lacking. So as I said before, in order to unlock the flexibility and face the challenges of the energy transition, then they need to modernize. From one side, they need to upgrade the grid in terms of capacity, so infrastructure investment, but also digitalization investment in order to unlock real-time operations. And in order to face these challenges, another motivation is that DSOs need to enhance their current role. Because in the traditional system structure, in academic terms, the DSOs were using to have a passive role, just regarding to the connection, disconnection of distributed energy resources, transform the high voltage to low voltage and then distributed. So a more passive role in the grid, while in the future with this increasing integration of distributed energy resources, they need to take an active role in the peak load management to distribute energy resources, network congestion management, procure voltage support, also to a better communication also with the transmission system operators and so on. So as you can see, DSOs is playing a vital role in the current energy transition. And among all the actors is the one that are facing lots of changes. And this is just a logical recap that I would like to show you. So as we know, as I said so far, DSOs are playing a pivotal role, and they need to empower their current roles through digitalization investment. However, nowadays, digitalization investment are still limited and partial. Let's think about, for example, the case of the smart meters, where the penetration rate around Europe is now increasing, but there are some countries still under the 30% of the penetration rate. And also when we are talking about the energy visibility, the visibility at low voltage level, we can say that we are almost blinded. On a use case in France, over an asset of 800,000 secondary substation, just 1% is digitalized. So we believe, and we make this assumption, that there is something that is actually hindering digitalization. And this is actually the scope of our research. So understand what is hindering digitalization and try to understand how we can face these challenges and which kind of methodology we can adopt in order to face these challenges comprehensively. And before proceeding, since we're talking about digitalization, it's also important to make some clarification here, especially in academic terms. It's important to distinguish among three different concepts. When we talk about digitization, these are common terms that we usually find in research articles, for example. When we talk about digitization, here actually we mean a simple conversion from analog to digital data. And the most simple example is, of course, when we want to translate a letter to a PDF file. Okay, so this is a process of digitization. When we're talking about digitalization, is actually leveraging the process of digitization in order to improve or empower a certain process, a singular process. In the case of the letter, for example, if I digitalize in a PDF file, then I will be able to send it by mail, and I will receive the response faster rather than I have to rely on posts, for example. So you can see there is an optimization of time here. And so this is more or less the concept of digitalization. But when we are talking about digital transformation, we are adding another layer of complexity, a layer of economics and social and business layer here, because we are leveraging this optimization through digitalization to implement new businesses. In the case of the energy sector, let's think about, for example, new emerging markets like a peer-to-peer energy transaction among the end users. You can leverage, for example, real-time operation unlocked by digitalization in order to create a new market opportunity. And this is digital transformation. However, when it comes to the energy sector literature, scholars usually confuse this kind of terminology. So they use, we retrieve more than 20 definitions and are all collected in our deliverable of the InnoCyPES project 5.1. These are just few of them. Sorry if it's not perfectly clear on the slide. But yeah, I just want to show you here that there are a lot of definitions used in literature where scholars use digitization to intend digital transformation or digitalization to intend digital transformation. What I understood from all the literature is that is a mix of components. So when we talk about digitalization, it's more or less we're talking about digital transformation. And in our research, we rely on a definition provided by the International Renewable Energy Agency that described the digitalization as an increasing application of digital technologies across the energy sector in order to achieve certain desired outcomes like improved safety, efficiency, and productivity of the energy grid. So that's what we mean by digitalization in our study. And here I just wanted to list you some digital technology, but also these are well explained. And also I will provide you some literature at the end of this, this presentation where you can go and dig more in depth of use cases of application of each of these digital technologies. But since we don't have too much time here, we'll just proceed in order to pass to the second part of this presentation. So once we acknowledge that DSOs are important for our energy sector, they do need digitalization, but they are still lacking their investment. Now it's important to understand what is actually hindering digitalization. And in our research, we find that there are 5 main barriers that can hinder digitalization investment in the energy district. And these are going from technical to human factor barriers. Here, just to go very briefly in parts of them. So for example, technical barriers refer to the limitation of the technology itself, so related to the integration of this new digital technology in an old network infrastructure, interoperability of different interfaces of digital application among also different DSOs. Cybersecurity is a technical problem itself, because when you are proposing a tool, you also have to guarantee that this tool is safe for the user. Scalability and replicability, but also there is a problem here, a very large problem related to the energy consumption from digital technologies. Because if you want to scale, then the amount of data that you need to store and manage in a huge data center is going to produce also, to consume also a lot of energy. So there are few technical barriers that can also hinder digitalization investment. Organizational barriers related to the lack of the organization itself, lack of awareness of the potential of digital technologies, lack of data sharing between DSOs, among the same DSOs, within the DSOs and so on, and also change management policies within the organization. And then here we come to regulatory barriers, and these are actually fundamental together to the economics barriers, as we will see later on in this presentation. As DSOs are a monopoly, operate in a monopoly environment. And in order to push their investment, we need a concrete framework of incentives mechanisms that push them to invest. Otherwise, innovation will be lacking in this monopoly environment. And we are experiencing here, but is a working going on actually at the moment at the European Commission, lack of standards, responsibility and obligation of DSOs, for example, in the flexibility market. So they do not know their responsibility and obligation in future energy and flexibility markets. And so they just prefer to go for business as usual investment, conventional infrastructure, rather than try to innovate and digitalize the grid and unlock new opportunities. And also lack of policies regarding security and data ownership of critical data of the energy sector. And we come to also economic barriers here, because DSOs are reluctant to invest because they do not understand properly the value of this digital technology. It's because it's a complex, actually, subject. And this is also one of the main motivations why also we decided to go for system dynamics, in order to better understand what is the real value of digital technology, what are the real costs, and all the benefits. But this, of course, Jose will explain better, more in technical detail, how the system dynamics work and how system dynamics can help us to better understand the value of digital technologies. And then we have, of course, human factor barriers, because we are lacking digital skill. Where we have conducted interviews, particularly in France, DSOs were telling to us that they would like to have a figure which has a knowledge on the technical aspect of the energy network, also on the expertise on digitalization. Because when they need to start a new digitalization investment strategy, they need to rely on a very expensive consultants company that are that have an expertise in digital technology. And this also contributes to inflating the cost of digitalization. And also, of course, there are all the concerns that are related to the use of AI, job dismissing, and social concern, and so on. So these are the 5 main barriers, but this was something new also in the literature. What we also did in our research was to understand how to prioritize these barriers, and we did it by applying this framework. So we acknowledge that actually DSOs are going to have new roles in the energy transition, in particular, summarizing in these 6 core functionality. And in all these 6 core functionality, there are different prioritization also regarding how to face these technical, organizational, regulatory, and so on barriers. So we try to understand which of these barriers need priority of action in each of these core functionality that can be enhanced by digitalization. And this was the distribution of the sample that we actually interview. So we try to pick up experts in each of these core functionality, and it was quite homogeneous. But yeah, what I would like to show you, and this is the most important thing, is that actually economic barriers are the one that need priority of actions for DSOs. And that's why then in the second step of our research, we decided to focus on this critical aspect, on the barriers that are hindering digitalization investment. And this is related to a certain number of factors, but actually there are 2 main problems here. First of all, the current incentives framework provided by the national regulatory authorities is insufficient, as DSOs were saying to us, and also how we proved towards our application of our model. And also another big problem is understanding the benefits of these digital technologies, because the DSOs are the ones that are responsible for investment in the network infrastructure. And when they are providing a digitalization investment, the benefits usually of this new technology is spill over among multiple stakeholders. And they are not able to monetize and also to track all these effect that the digitalization investment can have on the grid, and how this effect can have another link with the regulatory framework, and how the regulatory framework can also respond and create this loop, as we will see later on in this presentation. And this is actually the main motivation. So understanding better how the energy regulatory framework works, and how this is interlinked with distribution system operators' investment strategies, and also how to understand better the benefits and cost of digital technologies. And that was also the main motivation of our research collaboration. This is just to show you the main highlights of the first part of our research, where we acknowledge, as I said before, several barriers, but in particular, the economics one that need priority of actions because of the limited budgeting of DSOs. There is a trade-off nowadays that is actually pushing towards conventional investment because there is this capex heavy solution bias, and this is a fact. And also uncertain benefits provided by digitalization. On the other side, complexity of digitalization technologies and their assessment. And also, as Jose also will tell you, a limited scope of our conventional cost-benefit analysis. And that was the main motivation that also led us to use system dynamics modeling in order to try to unlock digitalization investment in power distribution grids by better understanding the regulatory framework and its interlinks with the digitalization investment strategy of DSOs. And we did it both in a qualitative manner with the use case that we started in Australia and also with a quantitative application in Portugal. So now I will pass again the floor to Jose to introduce you a brief introduction of the system dynamic methodology method approach. And here I also listed some suggested literature that could be useful for you if you want to have a better understanding of what digitalization can do in our energy sector, what are the main barriers, and also use cases of applications. Okay, so let's talk about system dynamics now.
Thank you very much, Roberto. It was exactly on time. So we take this. So we have seen what are the different barriers, what are the different problems. So thank you very much for the very nice contextualization of the issue we are dealing with. Because I would like to all of us think of this question. If you are a DSO and you have the goal and the decision of let me go here. You have the goal of digitalizing. So you make a decision of investing. So you assess how the state of the system works, how the system would respond, what are the quality of supply indexes, what are the operational costs, what are the investment costs. But would you stay there? Or would this be the only decision would you make? Or do you think your decision will be affected by others? I think all of us will agree that the answer is yes. So everything is much more complex than that. So our decisions are affected by others, are often affected by different delays. In time, we need to build a new transmission line, distribution line. It takes different years, 3 years, 4 years, 2 years, depending on how we implement. We are also affected by other DSOs because if they do it better and we are under a benchmark scheme, we do it worse than the others. We receive less retribution in the tariffs, and maybe we are going to be less incentivized to make a new investment. So there are different goals, different decisions, different stakes that we need to consider when we want to achieve such a goal, the goal of digitalizing the whole distribution grid. So think of this word, systems. So we are going to talk a lot about this, systems. So there are different examples of systems, not only distribution grids, but also now that we are in Italy, I wanted to show this, this slide. This slide, it's a short story. So this slide is about, it was made by the Club of Rome, a set of experts that gathered in the 1970s with this system dynamic new tools that were arising and so on. And they had a big challenge. So they had to evaluate what were the resources on the Earth, the population evolution, and how these resources would evolve during time to see when, for example, the oil resources would go down, or when would be the peak of the consumption of oil, or when the resources of the Earth would not be enough to supply to all of us, right? And actually, I wanted to ask, because this study was tried to validate it in the 2020, I would say, and they reached a very good conclusion, is that they were right. So the results match exactly what the estimations were in the 1970s. So look at how important it is to consider in these studies the system perspective and system dynamics. So we see that these systems exist not only in the global dynamics, but also in climate change. We see a very good example of feedback loop and complex system, but also in the power sector. And this is what we are going to focus in this presentation, specifically in distribution grids. So think about, sorry a bit for the ones present, because there are some bubbles. You can see it online with the colors, a bit more clear. But basically here, this subsystem A, the DSO, the business model, has different variables. So has the different investment decisions and has the total cost and total revenues that they would receive. Often, traditionally, the style of since Roberto anticipated that we are in a regulated monopolistic market, so the position of the DSO often, since they had privilege, we could say status when we have more information about the state, and so was to set and make the investment plan, send this investment plan to the regulator, and the regulator, that is the subsystem B, would define how much OPEX, CAPEX, and we determine the tariffs according to that. However, it's not enough also when we consider the new perspective and the new context that Roberto mentioned before, neither when we have the multiple, sorry about that, let me go back. When we have the multiple feedback loops that arise when we want to assess digitalization, whose value spills over multiple stakeholders, when we deploy different smart meters, the value spills over to the customers. When we deploy new digital substations, the value can also spill over to new, of course, the more easy penetration of electric vehicle charging infrastructure. So the value of digitalization spills over multiple stakeholders and generates multiple feedback loops. This, together with a more complex system, raise the need to consider much more feedback loops in the scheme. So much more complexity in the decisions, as also we anticipated before. So generalizing, what is a system? We all have a very good intuition of what is a system because in our human body is a system. So it's a set of interacting elements and or in this case parts of the body. But if we think about the distribution system, it's a set of actors, stakeholders that set and act according to the different rules with their different interests and have a different dependency on the previous decisions. So that's what we can consider as a system. And it changes over time. It's governed by feedback loops, by feedback structures, and we can observe that it's non-linear intrinsically. So all these interactions, delays, information gaps present and give us the complexity that we need to assess from a different perspective. So a systems thinking can create models, can help in describing the feedback loops within systems, and we will see how these models are useful for identifying problems and making more effective policy decisions. So in the distribution grid, very specifically, let me see, and let me quote three, or at least the first two. The first two are Euroelectric, EPRI, so two very big institutions related to the distribution grid that mention that distribution grid investment should increase an average of 33 billion to 66, 67 billion per year from 2025 to 2030. So this is a lot, a very significant amount of new investments. Also, EPRI says that within this investment part would go to digitalization, and EPRI mentioned a long time ago, actually, that the societal benefits of digitalization or smart grid can be indirect and hard to quantify, but cannot be overlooked. So this is what we see from the system. This is what we can observe. So all this news, all these quotes of the system, but can we really see why? Why does this happen? We would like to know how this happens, why does this happen, and what are the decisions that take towards these consequences. And behind these decisions, there are some structures. The structure of a system is what drives the behavior and what drives the consequences. So this exactly was what we want to analyze. So we want to see how this complex system that I mentioned before works and what are the specific variables that are hindering and hiding. Sorry about this. Sorry about the color again, but it's that all the pictures and yeah, so are described in more detail also in the presentation. But basically, this system is hiding multiple variables, multiple feedback loops that we need to unveil to better understand from where the money, the benefits for the DSO come from, where the costs come from, and how these benefits also spill over multiple stakeholders. So another consequence of what I mentioned before in terms of the investment, we see how institutions such as Deloitte split the amount of investments that we need to make per mode. However, how can some of you tell me how can each of these investments lead to specific benefits? What are the specific benefits arising from electrification of buildings, industry, electrification of mobility, emission-free generation, digitalization and automation? So these are big terms, big concepts, but I would like to know, I would like to disaggregate more what these terms from. So for that, we need to really, as I mentioned before, assess what are the different links that we have here. And here I have this slide that show what are the different methods that are existing right now in the systems literature to assess complex systems. Some of us know this discrete event process-centric modeling. So this is more related to low level, more related to, for example, power flow analysis, more related to planning in specific distribution grids. However, when we assess also different systems or different agents or the interaction of DSOs and the TSOs, we see also in the literature the application of agent-based modeling, which is another technique based on systems and is based on modeling what is the specific behavior of different agents within for example, a electricity market, for instance. However, we want to go more into the higher level of the picture. We want to go towards system dynamics that can provide us the abstraction level to match the big goals that we see from the European Commission or from the International Energy Agency with the reality of digitalization and the reality of the new grid investments that are required. And here is where system dynamics is the selected option for technology, so for as a methodology. What is system dynamics? Now we go into the specific methodology. So this is a modeling methodology that arises in the 70s, in the 1970s, from the MIT, from Professor Jay Forrester. Started this idea coming from control theory, from the idea of feedback loops arising from control theory applied to systems that are not specifically power systems or other systems related to power electronics, for instance. But in this case, it's to social systems, population systems, urban dynamics, or the evolution of climate change, for instance. So other types of variables that are also driven by differential equations, and that also by each of these blocks actually represents a differential equation, and how this differential equation actually lead to a changes in the behavior when we make a step or a response, and we see in the right-hand side slide. So system dynamics has this potential of assessing the high level and the high complex problem. And I wanted just to give you an overview on what are the main concepts very quickly. What are the main concepts of system dynamics in this case? So we have all these keywords: reference models, causal links, causal loop diagrams, feedback loops, model validation, simulation. Some of you already know from your studies, but I want to say that system dynamics has very standardized process in the literature that has been carried out for different years. However, I just wanted to clarify that the definition of the system comes with a process of qualitative definition. So we need to know and define the process, define the problem that we are modeling, and then start gathering data and, of course, executing and defining the different equations, validating these equations, and then simulating how the system evolves towards different scenarios, different policy decisions, or changes in parameters. And for that, I'm going to explain what are these main concepts are. So what is reference models? First, when we define system dynamics, we need to know what variables are we modeling. We need to know, for example, what is the evolution of electricity. In this case, what is the evolution of renewable integration? What is what is our people? What is the consumption patterns as we see in the electricity consumers, the final consumers, or what is the peak evolution of the consumers, or what are the population growth in the different areas, or what is the state of the grid that we have right now. So these are the variables that we need to know, and we mentally have to envision what is the different trend that we are going to see in these variables. For example, we have here on the historical data, what's the evolution, for example, the final electricity demand in Europe plus the UK, and there's the expectations from Deloitte till 2030. But also we need to have an idea on how these historical values could lead to expected values. Humans, we are very good at thinking about linear models, as forecasting linear models, but we struggle when we have to address non-linear systems. And that's a reality, right? So that's why we have so many good tools from control theory, from other theories to address these issues. So once I said this, and I mentioned that we have to go through qualitative, quantitative, validation, and simulation. So once we have identified what are the reference models, then we need to know, okay, what is going to cause this reference model to happen? What are the variables that are affecting this behavior? So we need to know and make a causal chain. So we need to think about cause and effect. That's one of the most natural reasoning processes that we have as humans, cause and effect. So let me say that in the legend, we plus case means the directly proportional relationship. So if one variable A grows, variable B will grow, and otherwise. And then inversely proportional means if variable A grows, variable B goes down. Okay. So think about grid loading rates. So how our cable is loaded? 20%, 30%. So depends on the consumption and depends on the power capacity, right? So we can say that more power capacity will reduce the loading rates. More peak power demand will increase the loading rates, right? We all agree. This is a clear causal chain. But what about length of vacation period? Could this change the grid loading rates? Would you say so? No, not really, actually. No, we need to find, actually, this is more correlation, what we call as correlation. So there's a difference between correlation and causality. So that's why we need to identify more the causal chain that actually affects there. So you were not wrong, but there is a missing part in the equation, I would say. So you need to identify the causal chain that is defining a specific phenomenon, a specific reference model. And that's what we know as causal links. These are the specific causal links. A set of causal links, let's go to the next step. So now that we understand this, let's go to the next step. So a set of causal links define what we call a causal loop diagram. All this, what we have defined there is a causal loop diagram. And when we add, for example, feedback, we say that more loading rates will trigger more grid investments. We could reasonably say that more grid loading could trigger new investments in one specific area. And we say that grid investments trigger more grid power capacity in the long term with some delay. We see that we have here a feedback loop. This is a specific feedback loop. What I have there in red with a minus, that is what we see a feedback loop. And what type, very quick, what type of feedback loop do we have here? So we have two feedback loops types. So our colleagues from control theory already know the answer, right? So we have two type of feedback loops. One that is, we say, stable, and what that is, right, more unstable, no? Or tends to goal-seeking behavior feedback loop, or one that tends to instability, right? So this is exactly what we define in system dynamics. It's absolutely the same. In this case, there is a very, very fast rule, is that when we see an even number of minus in the feedback loop, it's a positive, it's a reinforcing feedback loop. It's a, we could say, unstable, okay? So in this case, this is not the case because it's an odd number. So this is what we call a goal-seeking feedback loop, or in this case, balancing. So it's a feedback loop that balances the system. So it doesn't. So when we change some of the variables, the system tends to balance and seek the goal of investing. So let me follow the reasoning. So when we increase loading rates, we increase investments, we increase power capacity. That power capacity can reduce the loading rates. So we reduce the investment. Okay, so this we tend to not to tend to instability. Okay, that's the point. So feedback loop. What is a feedback loop? I anticipated. So what we had there, it was a balancing feedback loop. Okay, but what is a positive feedback loop or a reinforcing feedback loop? We have two good examples here. On the left-hand side, reinforcing, more employee skill, more customer satisfaction, less complaints, less complaint, more management time. Let's say, no, actually it's more complaints, more management time spent, right? So basically the idea is that this feedback loop tends to instability. This balanced feedback loop that we see on the right-hand side tends to goal seeking or tend to slow down at different processes in the system. No? So this is the principle. This analysis of feedback loops is the principle to perform a qualitative analysis of the feedback loop, qualitative analysis of the system. And this enables us to know if the system or what are the variables that are affecting one specific behavior. For example, if this feedback loop on investments, imagine, let me ask, if in terms of investment, we have multiple feedback loops reinforcing, affecting the new investments in digitalization, would you think that the system would go to incentivize this investment behavior, right? And if we have more balanced feedback loops, we would think that the system is reluctant or tries to slow down this new trend. So it counteracts new trends, right? So we have this intuition, this nonlinear behavior. It's a bit difficult because we are more comfortable with linear assumptions, but in this case, that's the reality. So we need to, when we carry out, and Roberto will explain that in detail later on, this qualitative feedback loop analysis, but this is the principle to carry out this type of analysis of a complex system. What if we put another layer of complexity? What if we go with on hand with our control engineering friends, and we go towards the equations and the differential equations, and we try to assess what's the evolution of the system. And so I don't want to show so many equations. I just want you to take a look at the right-hand side and see this analogy of reservoir analogy. So this differential equation, all these differential equations that we see here can be represented by this reservoir. So the reservoir shows the level of the reservoir is the state of what we call the state of the system. All the entrances to the reservoir are the inflows. So and the liters per second that we enter, these are the inflows and that we have within the integral that we see. So the evolution of the level of, in this case, is not a reservoir water, it's a fake reservoir. In this case, we mean stock of capital or as economic stock. But basically this idea. So make many reservoirs to model how the system will evolve as a whole, and then connect all these reservoirs to model the feedback loops within the system. And this is the principle of the quantitative system dynamics. Basically, we are talking with also our colleagues on data analytics, on smart meters as well, and we know that they have this process very well known on the validation of the system. You need to validate, you need to train your model, you need to execute, test, of course. And the idea is basically related to that our model represents the real behavior that we see in the real world also. But in the training part, we need to represent historical values. So this is what we perform. So we validate the model. Our model represents the real world. This we can do with different softwares. These are some commercial software that I'm not going to mention, but these are some commercial softwares. And this is the one we are focusing on here because it's open source, and we want to make everything open source in this project, right? This is a very fast overview. I think I know it's a lot of information, but I just wanted to give you a glance of system dynamics. You can read more. You can take a look at Forrester. It's a very nice piece of work, the handbook of system dynamics, more theory, more other introduction of system dynamics. But I think this gives you a little bit of speed in the process of understanding the qualitative one and the quantitative modeling. So thank you. So we would like to take a very quick break. Thank you very much for the attention. And in 10 minutes sharp, we would like to be back. So yeah, thank you and see you in a bit.
We are ready to start again the second part of the tutorial. And in this second part, we will talk about the application of the methodology in a qualitative use case. Okay. And this was a study that we conducted in Australia during our external research stay that we conducted from August 2023 and January 2024. And we have been hosted by the University of New South Wales in Sydney and also the Commonwealth Scientific, Industrial and Research Organization still in Sydney. And I really would like to thank you, all of them, and some of them are also present in this tutorial, for all the effort and support they provided to us in order to make this study happen, and also help us to interact with a lot of experts and provide us a lot of nice discussion that help us to improve the quality of our model. When we are talking about a qualitative application of system dynamic model, we need to follow a structured approach. And in our case, we follow 5 main steps in our analysis. And first of all, we start from the conceptualization of the model and building all the subsystems of our model. And this is related to understanding how the actors interact within each other, and what are the main variables, also as Jose was saying before, which variables we need to consider. And we start from a conceptualization, and then from this conceptualization, once we realize what were the main variables, then we apply this conceptualization to the Australian use cases. And we exploded all these variables within the Australian use case. And this was the step number 2. And then we pass through the validation of this conceptualization and the final causal loop diagrams that we developed. And once the model is validated through an intense interaction with experts, and you need several experts that help you to go through the validation of your system dynamic model, and in particular, different range of experts that come from, in our case, from distribution system operators, because they are directly involved in this process, national regulatory authorities, but also academic experts and consultancy industries. So we had the luck to interact with several aspects in our study. And once the model is validated, then you can retrieve, by running the model on this InnoCyPES platform that we will show you later, you can retrieve the feedback loops. And you can be sure that those feedback loops are actually tell you real information, because the previous model was validated. So all the links were validated. So all the feedback loops that we retrieve are supposed to be validated for our analysis. And then since we retrieved 296 feedback loops that can influence digitalization investments, we had to actually make an order there and characterize all these feedback loops. We had to assign a label to each of these feedback loops, and this was the most intense part of our research. It took actually some weeks, because it's an iterative process that you have to study 296 feedback loops. And once you start, you need to restart again, because you find a new mechanism, a new attribute to relate to a certain feedback loop. And then we develop a selection framework to select among all these feedback loops, 11 feedback loops that were reportedly discussed in a workshop organized ad hoc with experts to discuss in deep each of the feedback loop. Of course, we would like to analyze all of them, but there were some constraints related to the time that we were spending in Australia, the time at our disposal, the availability of experts time. So we decided to go for 11 feedback loops, which are actually very indicative and informative in our case. And it shows how this methodology, even though it's a qualitative application, can unveil a lot of information. As Jose also was saying before, one of the main strengths of system dynamics is to unveil certain causal loop relationship that you are not able to see. with a common methodology. And with this feedback loop analysis, we are able to unveil all these obstructive dynamics and understand better how is the system behavior. So the key word is to understand the system behavior. Okay, so concerning the step number 1, this is the final version of our conceptualization, similar to the model that Jose was explaining you before. So we have 3 main layers that interact within each other. And the key one in our case, in this case, because we want to make a focus on incentives mechanisms, is the regulatory subsystems, which is central in this conceptualization model. And basically, here we decided to represent all the variables that have an influence in the definition of the total allowed revenue of a DSOs. Because total allowed revenue is actually the key variable that the DSOs rely on in order to then have a certain investment capacity to invest in certain investment strategy. That could be a digital investment strategy or a conventional infrastructure strategy. So here, as you can see, we mentioned just some of them, but we have certain remuneration schemes related to the capital expenditure or operational expenditure, incentives for innovation, performance-based regulation that have an influence in the definition of total allowed revenue. And also the majority part of regulatory framework around the world, to define the regulatory frameworks, they define a building block approach, which is composed by 5 main voices. So the total allowed revenue is usually consisted of 5 main voices, which consist of taxation, the depreciation, the operational expenditure, the return on capital, and certain adjustment from incentives mechanism. So this is just to let you understand that in this conceptualization layer, we decided to put all the variables that have an influence and impact on the total allowed revenue of a DSO. And then we have the distribution system operator subsystem, and we wanted to make crystal clear the difference that we have between conventional investment and a digital investment, because the additional value that we would like to bring to the audience in our research is to understand to what extent a digital investment is better than a conventional investment and vice versa. And we want to do with a better understanding of the system through our system dynamic application. And so here you can see there is this distribution system operator layer divided in 2 main blocks related to all the effect that the digital investment strategy can have on the grid and how this is connected to regulatory subsystem. And then you have the same thing for conventional investment. And then we have the final grid user subsystem, because all this is driven by the necessity and the challenge that we need to face on our grid. So what is our power demand? What is the future demand flexibility that we are going to have, the number of customers per voltage level, and so on. So this is our conceptualization that can be applied in different contexts and be exploded. And we applied this in Australia. But we started from this first sketch. This is actually one of the first sketch, but I wanted to show you just the logic behind this study. So we have the total allowed revenue that can be influenced by the regulatory environment through a certain kind of investments or the definition of the building block approach. And through this total allowed revenue, then you can make different kind of, you can follow different kind of investment strategies. So digital infrastructure or in physical infrastructure, and they can have certain effect on our grids, and then they can eventually come back and retrofit to the regulatory subsystem. So what we are going to show now is the application of this conceptualization to the Australian use case and show you how we exploded the total allowed revenue, the incentives mechanism schemes, and also how we exploded these 2 main voices of digital infrastructure and physical infrastructure. And this is the final version of our regulatory subsystems. We'll use the point. So as you can see, the allowed revenue is influenced by, in particular in the case of Australia, by the building block approach mechanisms, which is consisted of the operational expenditure, the taxation, the return on capital, which is defined by the revenue asset based, and the depreciation. So these are the four main terms, plus this revenue adjustment from incentive schemes. And in our study, actually, we are focusing on this contribution to the allowed revenue in particular. So understanding how we can change our incentives mechanisms in order to have a huge impact on allowed revenue, and so provide more investment capacity for DSOs. And the strength also of this visualization is that we can see also the interaction with other subsystems. So, for example, if DSOs decide to make an investment strategy, this investment strategy has an impact on the grid, and this is somehow interacting. For example, an investment strategy can cause less number of failures, and this allows the DSOs to access to a certain incentives mechanism, both for a reward or for a penalty. But both can then have an impact on the allowed revenue. So this is what we tend to represent with this causal loop diagram. So the interaction between regulatory subsystems and investment strategies from the DSO's perspective. And this is the overview that is missing at the moment. And this will help DSOs to understand and to track all the benefit and causalities that different strategies can actually have on the grid. And we did the same for the other subsystems. For example, this one is the digital block within the DSO subsystem. Just to explain you, for example, a basic logic here, a basic feedback loop that you can retrieve. So you start from increasing investment in digital assets. So your stock of digital asset will improve. You have access to more data generation and analytics tools that can unlock a lot of several opportunities for congestion management, reducing the probability of failure. And this can have a chain of effect that eventually can retrofit also in the regulatory subsystem and can cause a reinforcing feedback loop for investment in digitalization or a balancing feedback loop. So there are a lot of cases where if you, paradoxically, if you want to invest in digitalization, then you can cause also a chain of effect that can lead you during the time to have less investment in digital investment in the future. And these are those kind of dynamics that we would like to provide an overview in our research. And this is the same thing for the conventional investment subblock. So the logic is the same. So we tried to explode these blocks and applied it to the Australian use case. And the same for the final grid user subsystems. So these are the two steps that that have been running in parallel to the validation, because this is an iterative process. This is the final version of our model representation, but this has gone through an in-depth validation with expert interviews, and this came to the next step. And here I also would like to show you some tricks on how we prepare these interviews that actually in a qualitative analysis are fundamental in order to validate the analysis through expert overviews. And the first thing is, of course, to think about which stakeholders you need to involve in your analysis. And this is not a trivial, actually, decision, because you need to understand which contact you can leverage from your network, what is their availability. But regarding the domain, we decided to stick with the distribution system operators, national regulatory authorities, consultants company expert in the energy transformation in Australia, and also the scholars' perspectives. That also is very important. And when you are dealing with system dynamics validation, as you can see, system dynamics is very complex to understand at the first glance. So for us, since also we had just 1 hour for our interviews, it was fundamental to save time as much as possible. And we wanted that our interviews arrived prepared to the appointment. And so that's why we decided to provide a comprehensive and informative booklet prior our interviews that introduce the scope of our research, and also already has a set of questions that we're going to ask to our interviewees. And then we send the interviews request at least 2-3 weeks before, and the booklet was attached at least 1 week before the interview. And this is the the sample of experts that we actually interact with, for a total of 27 different experts that contributed to the model conceptualization and validation. So that big scheme that we see with the 3 layers, and also all the exploded schemes of the subsystem of our model were validated through this set of interviews that were group interviews that sometimes had different organizations interacting. And this was actually very useful in our analysis because it allowed us to still have, in every moment, a systemic perspective and a confrontation among different stakeholders on how they intend a certain dynamic or not. And this added a lot of value to our analysis. And this was possible with a strict interaction with the Australian energy regulator. And here I just also put some suggestion if you want to conduct an interview-based analysis. Beyond leverage or network opportunity, it would be nice also to be proactive in retrieving your contacts. Because, for example, we were reading reports from the Australian energy regulator, and there were names cited under the report. We just sent random emails to everyone without any hope. But then they respond to us, and they were interested in our research. And this was actually fundamental in our analysis because it allowed us to have a lot of contacts that help us to improve the quality of our research. And this is just to show you an example of the booklet. So this is the overall structure. The booklet was composed by 16 pages. And since the interview was complex because they need to understand that schema that I showed you before, right? The causal loop diagrams of the single subsystems, it was fundamental that they have a read before coming to the interview. So we provided a comprehensive booklet with all this information where we attached the diagram and all the questions that we were going to ask. This is an example. This is one of the first draft of the regulatory subsystem, and we attached a description of the regulatory subsystem and also a range of questions that we would like to have answered by the experts, in particular related to certain specific links that we were unsure, because some links we were able to retrieve through the literature, some others you are not able to find these links through the literature, and you need to rely on experts' points of view. And then once this model is validated, then you can finally retrieve your feedback loops. And we retrieved 296 feedback loops by running our causal loop diagrams into the InnoCyPES platforms. However, a shortcoming of this platform is that regarding the causal loops, the feedback loop analysis, you are not able to use, they just list you the feedback loops, but then you are not able to use research tools to understand if you want to find a particular variables in these feedback loops, you are not able to do it. They just list the feedback loops. So for us, it was important to have this tool at our disposal. So we copy and paste all that list of feedback loops and move it to a Word file where we were able to adding notes and our consideration to each feedback loop and starting the labeling process, because we wanted to have, as you will see the complexity later, each feedback loop is composed by main variables, and a feedback loop can be reinforcing balances. So we wanted to have a label that were able to communicate to us instantly what kind of feedback loop we have in front of us, what kind of mechanisms are making him reinforcing of balancing. And this was actually an intensive part of our research. It took maybe almost the majority part of our time to understand how to label this feedback loop, but this is also a value of our research provided this methodological approach and also a way to labels feedback loops. Then once we finished all this labeling process, we moved to Excel in order to speed up our research of feedback loops and then start our selection process. Try to be as much objective as possible, and then I will show you how we design our selection framework in order to be objective, because in a qualitative analysis, sometimes it's difficult to be, the line between subjectivity and objectivity is very thin. So it's very important to understand and communicate the framework that you developed in order to make your decision in an objective manner. And then we were selecting this feedback loop and discussed this in a workshop. And then I will show you some outputs and how we conducted the workshop. But so how do you retrieve the feedback loops through InnoCyPES platform? This is the main page of the software. You can see our model behind. And if you click on this icon with this luggage, then you can click on identify the loops. And here is the list that I was talking you about. So you have gray arrows that are indicating direct proportionality, and then the red one that are indicated an inverse proportionality. However, the software is not indicated if it is a reinforcing feedback loop, if it is a balancing feedback loop. So we needed to label on our own all the feedback loops. So we decided to move on this Word file. And this is how it looked like. So you have a set of variables connected by arrows. So in order to make clarity and understand at the first glance what kind of feedback loops we have in front of us, we need to develop this label. And then I will understand how we developed this label. But you need to understand that here is what a feedback loop is about, right? We start from an increasing of digital assets, digitalization investment. This will cause a certain cause of effect that will come back to the same variable. See, and this can cause a reinforcement, or so this could be positive, but also negative for the same variable. But how these causal chains, which mechanism is driven these causal chains and lead to a reinforcement or a balancing? Then we try to understand through our labeling framework. And this is how we differentiate feedback loops. First of all, we need to understand if a feedback loop is just contained by a single subsystem or is interact among multiple subsystems. So in this case, we are talking about respectively of a local feedback loop or a global feedback loop. And in our research, we are interested in global feedback loop. So this is because we wanted to provide a systemic perspective and understand how the subsystem interact with each other. So this is already an important attribute to assign to a feedback loop, understanding if it is a global or local. Then understanding what type of feedback loop that could be reinforcing of balancing. And then we have the loop variable, the one that I showed you before. So is the initial element in the causal chain and the final element of the final chain. This is what is the loop variable. And the loop variable can be digital investment or conventional investments, or can also be others variable. But in this study, we are not interested in other variables. We just want to have an overview of the behaviors that is induced by digitalization investment or conventional investments. And then we also decided it was important to distinguish another type of feedback loop, which is the hybrid one, where is a feedback loop that contains both digital investment variable and conventional investment variable, because it's also important to understand how a digital investment can have an effect of conventional investment. So that's why it was also important to distinguish also this other of feedback loop. And then we have the mechanisms that define how a system loop became reinforced or balancing. So yeah, defines how the feedback loop becomes reinforced or balanced. For example, an increasing of grid performance can lead to access rewards from incentive schemes, which can incentivize DSOs to invest more in digitalization. But what kind of performance we're talking about? What kind of incentives mechanisms we are accessing through these increasing performances? And these are all the information that we can retrieve fast through these label mechanisms. And then we have the sub-mechanisms, which actually specify in detail, as I said to you before, what kind of performance we're talking about and what kind of incentive scheme is involved in the feedback loop. This is actually complicated to hear, but when I show you, for example, an example on how we apply this label. So this is a case where we have a single feedback loop, so a feedback loop that is not hybrid, that not contains both digital or conventional investment. So as you can see, the information that we can retrieve from this label is that we are dealing with a feedback loop which is global, so it's interacting with multiple subsystems, which is reinforcing. And in this case, the variable is digital investment. So we have a feedback loop that is actually beneficial for digitalization investment. And we wanted to add also another information. So this I for us is digital increase. Yes. And then we have to understand why this is a reinforcing feedback loop. So what is driven this? So this reinforcement is driven by an improvement in performances, which allow us to access certain rewards from this capital expenditure share scheme in Australia, so a CapEx remuneration scheme. So you can understand that in a single line, we have a lot of information regarding a certain feedback loop. And this was actually fundamental to speed up our analysis, make an order, provide a framework to categorize feedback loops that it was still not in place in the literature because we were not able to find that. And yeah, and also was fundamental for the selection process of feedback loops. And then here is another example of an hybrid label that we applied with feedback loop. In this case, we have both conventional and digital investment involved in this feedback loop. We have a feedback loop that is global and is balancing, so it's not beneficial for digitalization investment. Why? Because this digitalization investment is causing a reduction of conventional investments, and this reduction of conventional investment is causing a secondary effect that lead to a reduction of digitalization investments. So this is the information that you can retrieve in this line. And this reduction of conventional investment is driven by increasing performances of the grid. So for example, with digitalization, you can improve performance without over-expanding the grid. So you reduce the capital expenditure. But of course, this reduction of capital expenditure can have an impact on your revenue asset base. So in the building block scheme, which also include revenue asset based, you have this secondary effect that can have that can be obstructive for our digitalization investments. And we identify 128 labels in total that we list in our Excel file. And of course, I just wanted to post it all the type of loop variable that you can have. So we have digital increase digital or conventional increase conventional, and also hybrid loop variable. And all the type of mechanisms that we can have in our analysis, so related to performances, the building block, as I said you before, but also relating to the management of targets of performance of DSOs and so on. The cybersecurity is also a mechanism that can influence digital investment. And then this is also the set of sub-mechanisms that we developed. And these are tailored, of course, to the Australian use case. So here we list all the incentive schemes of the Australian government and also other kind of sub-mechanisms. But what also is important to understand is that certain mechanisms can be coupled just with certain sub-mechanisms, and we provided this information here. So if we have a label that show P as a performance as a mechanisms, then this can be just related to this certain kind of sub-mechanisms. So for example, For the first one, an increasing in performance can cause a reduction of operational expenditure, for example, less maintenance, for example. And then you can access benefits from these other incentive schemes that is related to the operational expenditures, which stands for Efficiency Benefit Sharing Scheme in Australia, and so on. Then we also have, for example, mechanisms related to the target, so the management of targets that DSOs actually have, because when they have a set of targets, this defines their strategies. And sometimes this can cause a delay or an anticipation of certain kind of incentives of investments. And this is also a key problem that we retrieve in our analysis, because actually based on these, for example, forecasted OPEX or forecasted CAPEX expenditures, then DSOs are allowed to have more total revenue or not. And so this play a key role in defining the digitalization investment strategies in general, but in particular for digitalization. And this is also another kind of example of a coupling that we can have. This is the Excel file that we developed in the end. It's not crystal clear from the slide, but what you need to understand is that just we have all the feedback loops that we have identified. And for example, if we wanted to study just the feedback loops that involved the remuneration scheme related to the CAPEX, then we can just filter in here that we want, for example, just the feedback loops that show the capital expenditure sharing scheme mechanisms, and then we can retrieve automatically all this feedback. And this was actually fundamental for our selection, because in this way we're able to retrieve the total number of feedback loops showing a certain mechanism, so showing a certain label. And as you can see, this helps us for the selection, because we focus just on the feedback loops that are actually most present in our analysis. In this case, for example, from this screen, you can see that compared to the other labels, these labels appear 24 times in our analysis. And here, however, there is another problem. And the problem is that there are 24 feedback loops that show this label. So which one of these feedback loops we need to select in order to be objective? In this case, we decided to select the feedback loops that show the most variables involved these, because the majority part of these feedback loops are contained, nested in a bigger feedback loop. So we decided to take the bigger feedback loop because it's more informative for our analysis. And this ensured a selection process that was objective based on quantitative numbers that we retrieve on a qualitative analysis, of course. However, we needed to focus our attention just on certain aspects on our model, because we were not able to consider 296 feedback loop. So we built this selection framework. So we decided to focus just on feedback loops that show this kind of incentives instruments. So CAPEX, OPEX remuneration scheme, performance-based regulation, and incentives for innovation. So this was the first layer that we adopt for our selection framework. And also we decided to focus just on certain feedback loop typology, the ones that are actually hindering digitalization. And these are these main three ones. But then in the second stage, we also decided to provide an additional information and also analyze some feedback loop that actually already reinforcing digital investment, and understand how we can empower and enhance this feedback loop already in place. So that's why we decided to add this additional column on reinforcement digital. And here you can see all the feedback loops that we selected for our analysis. And this is an example of selection that we have done. So for example, here, this cake shows all the balancing hybrid feedback loop that we retrieved in our model. Among these, there were these two main classes of feedback loop showing a certain kind of mechanism and sub-mechanisms. And in order to assure objectivity in our study, so we focused just on these two that were most present in our analysis, for example. And among these that were showing a certain mechanisms, there were 12, for example, that show a certain sub-mechanisms related to the revenue asset base. So we picked up from this label the feedback loop. In particular, the feedback loop that was showing the largest number of variables. And now we move towards the most interesting part, actually, because once we selected this feedback loop, we started our discussion with experts in the workshop. It was an online workshop that we conducted from Canada when we were conducted our research stay at University of British Columbia, and the stakeholders were in Australia. So it was actually not easy, but we tried to make it as much as interactive as possible, and actually it was a success because we were able to retrieve a very informative discussion and retrieve a lot of usable policy recommendation that will help us to understand how to face these obstructive dynamics that we developed. And this is an example, and also for the workshop. Before arriving at the workshop, we sent another booklet showing all the feedback loops that were selected, a comprehensive description of each feedback loop, and already a set of questions that we wanted to answer related to the feedback loop. In particular, to what extent this feedback loop can influence DSOs investment decisions, and what kind of policy recommendation we can put in place in order to overcome this obstructive dynamic. So this is the logic that we used and applied in our framework. And this is an example of analysis that we conducted. So for example, we were showing this feedback loop, and you can see now the complexity of these hinder dynamics in our systems that are there, but we are not able to see it. And thanks to this system dynamic model, we are able to retrieve this in a graphic manner. So this is a global feedback loop balancing, and in particular is an hybrid. So we start from digital investments, and this of course can unlock data-driven decision-making, for example, tools that allowed us to unlock flexibility initiatives on the grid, with which we can decrease power consumption per voltage level, and also degrade the power element and also the loading rates. And actually, if we reduce this, then we can also say that we can increase somehow the grid remaining useful lives. And if we increase the grid remaining useful life, then the probability of failures will be reduced. And so we'll reduce the number of failure, the operation and maintenance costs. But also, in this case, we reduce the need to invest in conventional assets because we are unlocking flexibility opportunities. So we don't need to overexpand the grid. However, this will reduce, this will cause a reduction of the revenue asset base. And this is causing a secondary effect because the expected RAB that is used to define the total RAB revenue then will be decreased. And then, of course, you have less allowed revenue, less investment capacity, and less willingness to invest than in digital technologies. And this is kind of an information that we can retrieve from our analysis. From the expert overview, this is a feedback loop that can moderately influence the DSO's investment decisions. And then for each of these feedback loop, we propose different options to face this feedback loop. And we asked our experts to categorize these options and see which one were the most useful in order to face these obstructive dynamics. So you can see how efficient could be this methodology in order to understand the behaviors and try to retrieve policy recommendation in order to increase, in this case, digital investment strategies. And this is another example where actually all the stakeholders agreed that this was a significantly feedback loop affecting the DSOs investment decisions. I also forgot to mention that all the participants of the workshop were already involved in previous interviews. So they were already they already have a lot of knowledge about regarding our model and how the model works and how the system dynamics methodology works. And they also contributed to validate the model. So in this case, for example, we have a reinforcing feedback loop. So a beneficial feedback loop for digital investment. So if you increase the stock of digital asset, you can increase the data generation analytics tools, and this can unlock methodology to reduce, to improve the operation and maintenance, for example, strategies, and reduce the probability of failure. So there will be a decrease of operational expenditures from digitalization strategies. And then this reduction in the operational expenditure can lead to access to certain rewards in our incentives schemes structure. In this case, the demand management incentive schemes in Australia that actually allow innovation projects to be put in place. And with this, we can increase the allowed revenue, increase the investment capacity, increase the knowledge regarding digital technology, the technology maturity, and so on. So increasing in the future the willingness to invest in digital investment. So this is a positive dynamics. And also here, we also try to propose options that can somehow strengthen this feedback loop and also rate them with the expert points of view. And then from this, the final output of our research is this table, which is actually not crystal clear, but I just want to show you that these are all the main policy recommendations that we were able to retrieve from this very informative analysis regarding how to update incentive schemes mechanisms that are currently lacking, what kind of cybersecurity measures we can integrate to increase the willingness to invest, encouraging also innovation and system flexibility through innovation funds and so on. So, and also we mentioned what kind of feedback loop and dynamic we were tackling with this policy recommendation. So to conclude, this qualitative analysis is very powerful because it allowed us to identify key feedback loops that can both reinforce or balance digital investment strategies in power distribution grids, facilitate stakeholders engagement also with our group interviews among several stakeholders. There was a very nice exchange of knowledge among them and us. Improve the understanding, and this is the key factor in this research, improve the understanding of how the regulations through incentives mechanism impact on those investment strategies. And we show with these dynamics that we developed. Maps, these are nonlinear relationships. So we maps 296 nonlinear relations that can have an impact on investments. And this, of course, will support strategic decision making for DSOs and national regulatory authorities. And also our framework is adaptable for can be used in different countries because we developed this conceptualization, then we can just explode this conceptualization model in another country and then assess the dynamics for another countries and actually compare. Still in a qualitative manner, but still in a powerful powerful manner. And this is actually all for this first part of this tutorial on how we applied in a qualitative manner a system dynamic methodology and what kind of information we're able to retrieve. And all these studies is summarized in this journal paper. Actually, now a preprint is available. It's currently under review for a utility policies journal, where me and Jose actually intensively collaborated in order to have it done. So if you want to take a look, please, you are free to actually send us an email if you want also to go much more in deep and to have additional information. Thanks a lot.
So I would like to continue the presentation with the quantitative application. So I was receiving many questions about how correlation and causality are modeled in a specific case and quantitatively. So I would like to show a little bit on the construction of these models, but first, so I would like to show an example of how to construct a simple system dynamic model, and then we'll continue with showcasing a large-scale system dynamic model that we did in this case for the Portuguese case, where we modeled the business dynamics of the main Portuguese DSO, and we make a large-scale model from which we could extract many interesting results at the end for the DSO, impact on digitalization and conventional investments, and also the impact on end users and the impact on tariffs. So regarding the example of constructing this system dynamic model, so a model needs to represent with the least amount of equations and the maximum amount of accuracy the reality of a real system, of a problem, and needs to help to solve a problem. That's very necessary. So here we were focusing on the areas of the DSO, the subsystems that we described before within the DSO part, seeing how the operation costs evolve, the required investments or the revenues, and what are the tracking and finding what are the causal change from them to make these stock quantitative models, if we recall the first part of the presentation. So how to generalize a system dynamic model for any generic company. So we could model the dynamics of every company. So first, I would like to come to the field of business dynamics and the departments of business, where they study this or they identify a company in generic as the combination of different dimensions. The value creation dimension, which means the infrastructure of a company. What are our resources? What is our set of, for example, in the distribution grids? What are our cables? What is the status of our grids? What are the operational maintenance elements? What are the difference of numbers of stations, the length of the cable? So all this is what creates our resource, our infrastructure. The value proposition is what we know as the customer side. So how the customer side is handled in terms of what products do we sell, in this case electricity. But it's not sell, but it's a service that we need to provide as a regulated utility. Yeah? So what are the tariffs at which the electricity demand is tariff, and how this brings to the revenue? So this is a very generic structure. And then how aggregating all the costs and all the benefits this brings to the cash flow. Let's say what is our bag as a company in terms of benefits and costs. So, and how this bag is emptied when we invest or is filled in when we receive the benefits. But to this, you can say model, we need to add what is the digital part. How the digital parts that we have in the infrastructure, so in our resources, that means our sensors in the grid. That means our data analytic tools. That means our data cleaning, data unification, and data refinement process that we have from all the data from the assets. Or what are our digital products? If it's something that deals with the customer attention, or is it something that deals with another solution that we can sell to another provider? Okay, so this is the generic structure that we borrowed from the business field. And in this case, we need to add the regulatory framework to the regulation of the tariffs and the revenues, and also these three acronyms that we have here that are related to how good an investment is. So net present value means during time, with discounting and accounting for the value of money over time. So how much a specific investment or an action that you make in your company brings to net benefits. So you aggregate all the benefits, all the costs over time, and you reduce everything to a single metric that tells you if it's good, if it's bad, or how our system is evolving, right? The levelized cost of the energy is very common for wind. Our colleagues from the offshore wind introduce levelized cost
which is one of the main variables to define how much cost is the cost of a project that provides energy, and what is the evolution of the electricity price that it's going to be sold from this utility. And the last metric is the internal revenue rate. So it's also equivalent to the net present value and tells how profitable an investment is. So is the way to evaluate investments. So for this simple model development, once I have set this generalization, I will come from this ghost InnoCyPES model, which is more a very more simplistic part of the model. I will first showcase the definition of variables. Stock and flows will go together to the InnoCyPES tool, and then we will add data and try to build a simple feedback loop. Of course, doesn't represent the complexity of the model that I will show later, but I will show how to build the variables and start selecting and playing with the InnoCyPES tool. And then third, I will show how to, for instance, in this case, not validate because we don't have time, but just show how this leads to different feedback loops, this causal change, and how we can envision this causal change in the future. And you will see that this simple structure, which is very, very simple and will be very easy to follow, will be the constitute on the basic unit that will be replicated many times with this generalized structure. So we will have many feedback loops, many units of this that will constitute the big and the large scale model. Okay. So hands-on. Let's open, please, the InnoCyPES. Go to the Google page, InnoCyPES. If you have not registered, please register if possible. I will also guide you through, and we can do this together. Huh? But it's better if we can have it open. So we will go to the InnoCyPES website. Let me go back. We go to the InnoCyPES website. We'll create a profile. And then I will do as I'm saying. So we will go to the InnoCyPES file. And first, I want to show you so that this tool, it's an open source platform that is not only for system dynamics, but I mentioned before agent-based modeling. So we could also make agent-based modeling. And it's just a visual representation of differential equations, and you can include other type of equations and so on. So you can explore insights. So there are public insights that expert academia share in the InnoCyPES platform. You can see here in Explore Insights, we can see different type of models from population growth, environment. In this case, if we focus on energy, we can see some of the models that different people is working from vehicle to grid. This is one very nice example that we can find in the literature, and we can see, for example, how the different variables connect to each other, how this part that we said before that represents a state of the differential equation is affected by inflows and outflows, and we can see how for example, in settings, we could set simulation start, we could set simulation length. If we want to simulate per time, seconds, minutes, hours, what is the time step, and what is the simulation algorithm. And here, for example, if we take a look at the manual, they recommend Euler's method for agent-based modeling and Runge-Kutta, fourth order Runge-Kutta for system dynamics in this case. So this is the recommendation from the InnoCyPES tool. So these tools provide here a set of slides. So do you see the slides here? Yeah. So here is where we could change and define our scenarios. This is a scenario that was predefined by this author, but basically here we can simulate our model. For example, in this case is vehicle to grid simulation, but we could also simulate it by changing different parameters. So we could see it's very nice. We can see in real time how changing this battery size, battery size, months, we could see how the different results change. So, but this is just to give an example. Let's jump into our model. Yeah. Okay. Yes. So when we are here in home and we create a new insight, we click in create a new insight, you will see this. So you will see in getting started, schedule model, you have a clear overview on how to make a new model. Here I call it example versus one. Of course, important is to say is that you can save it as public or private. Private, you will be having it in your own or mini private repository, and public, it will be shown in this Explore Insights, what we showed, and with a specific tag that we include, okay? So let's define it public, so up to, yeah, so for now. And here, all this information I will try to summarize very fast. So let's clear this canvas. And what they call primitive here in system dynamics, so they have different elements that we can add to the model. It's like our set of toolbox. So we have elements to add to agent-based modeling, agent, state, actions. We can add pictures, design, text. But let's focus on these three: stocks, variables, and converters. So what is a stock? Yeah, so here, this stock, for example, it's we could define it and change the name. For example, it could be, yeah, we can say the grid length of the assets, because it's an state that we take a picture of this variable. So we need to see what is the level of it during time and how this is affected by the flows. This is what before we were including. This flow would represent additional increase of length per unit of time. In this case, if we go to the settings and we define years, we have it defined already, and we can define maybe 10 simulation years, or the fourth order Runge-Kutta because we are doing system dynamics. We apply, and then we have the simulation already settled. So we could start driving and building the flows. Input and output flow. So by these flows is how this stock will change. So imagine of it as a deposit of water. So we need to, what does a deposit of water have? Of course, have an initial value. We need to add what's the water in it from the beginning. Let's say 1 exponential to 9. And in terms of liters, imagine it's a very big deposit. And then we can say we have a flow in rate of 1,000, and we have a outflow of, we can say 90, okay? So I just want to see this evolution go down. So what if we simulate? Of course, we see the evolution of the grid length in this case. You see the grid length evolution per year and how this evolves per unit of time. Let's find a more lower value. For example, let's do 10,000 as an initial level. So we could see more this change over time, okay? So say it again. Yes, how to do the arrows, yes. So you just open the primitive, make a new stock, and from the inner part of it, you will see an arrow, yeah? And then extend it to the side, okay? And yeah, yes. Thank you, Roberto. Yeah, can we just see more properly? Yes. Yeah, sorry about that. I from here it's like I'm used to the same Zoom. Yeah, but now it's clear. Huh? So we could make a flow, inflow and outflow. And if we want to change the polarity, so the direction of the arrow, just need to click in the arrow, and yeah, so we can just click in the arrow and change here, reverse connection. Yeah, so here we could change the flow. Let's move it so we can see it better. Okay, so we could see how, for example, in this case, the level of the grid length of assets go up, and the other one goes in 0 because we have not defined anything yet. So the stocks is what gives memory to the system. It's what allow us to integrate actually. So it's what enables us for the system to make recursive relationships, to make the feedback loops. Okay, so for example, let's delete that one because that was an example. Let's give here a name of, in this flow, we can do it here also, additions of grid length. Yeah, so I often take a note here and add, for example, gigawatts per year that we add. And here we could say or that we can say depreciation of grid length. Sorry if its length is not power here, so we could say kilometers, huh? Yeah, kilometers of length per year. Kilometers per year. Okay, so this is in terms of kilometers. So what should we do if we want to represent different voltage levels? Reports of the DSO, we need to go to the reports of regulatory agency and take a look at how much are the grid length evolution per year in our validation period. So we need to see this evolution and how to compare. For example, imagine I want to compare my grid length for validation. So I simulate 10,000, 80,000, okay, to the historical grid evolution and how to input this historical grid evolution, okay. So there is this element that is a converter. Let's build a converter and ask any question if there is any issue or something, okay? So this converter, we can say, is historical grid length, for example. And here we see a plot for the different year, for the simulation time that we saw. So this allows us to do two things. One, to have historical data per year. So we could add here, if imagine the historical length was from 10 exponential to 4 and was progressing linearly to 20 to 4. Yeah, so we will see here how is the evolution per year, and it already interpolates from us. So it already facilitates the work. So if we want to imagine we want to compare this historical grid length with the two. So we have, let's say that is a bit smaller. Yeah, so I can change it by doing this. I wanted to show you step by step so you could see all the areas. So now on the moment, but I have some small models prepared so we could go faster. Yeah? But just to show you. So you see now we could simulate and compare historical grid length with the evolution of the grid length that we defined in our model. Okay, so this display, we can configure it as we want. So we can take it out, we can display these two arrows is addition. So this represents flow, this represents converter. So we could represent the evolution of everything that we want, the converters, the length, and show the points and show lines. So we could make it as interesting as possible, okay? So this is one of the main ideas. Also, we could do other interesting things. So we could explore the results. So by clicking here, we could do one thing. So we could explore the model just by scrolling on the different elements. We could see the evolution of it. So it will show a plot. Let me show you how it is. So we will collapse this, and just by scrolling, we will see directly the plot. So we could scroll and see our model very fast. What is the evolution of everything? Very fast. So we could validate, check, and everything. And what happens? This saved the status of the model with that set of parameters that we had. But what if we want to change the grid length? So, and what if we want to do it with the slider and with the different scenarios? Yeah, so we select the element. We can click here on this value slider. Okay, and automatically it shows here in the model. So automatically we have here the scenario that we could define. So now it's here. So imagine we can say 20,000 and we simulate. Okay, so the scenario changes and we could press the same button and see the two scenarios. So we could compare very fast the two scenarios and how the whole model can evolve over time. Okay, so this is just to show very basically how the system dynamic work and how this validation and simulation could be performed. Okay. There are other type of variables that affect our stokes. Okay, so these are, it's a normal variable. Here we could define what is affecting the different grid length. For example, like we could say that yeah. So this depreciation, for example, the depreciation. So what can affect the depreciation of the grid length? Well, we can also define a more systematic rule, an equation to define this. So equation, we can define it here by adding mathematical functions, vector functions, strings. So we could define the equation we want for our different flows or stocks, okay? So for example, we say a depreciation time So we could also define, imagine the depreciation. So we could assume that the whole length of the assets will depreciate, and we will lose the whole thing in 30 years. So the whole thing would depreciate in 30 years. This is just as an example, okay? So we click here in link, and we are able to connect variable with flow, or with variable with other different primitive, okay? So the depreciation, for instance, we can change it to the grid length of assets, which is this stock, this represents a stock, divided by the depreciation time. Okay, so we could see that how the depreciation now in length has changed completely, and it represents the values that we want. Okay, so this is just very specific and very simple example on how to play with this system dynamic model. So let's go to another part, which is example 2. I already here created a more, let's say, it's going to be a bit more interesting in the sense of we have two stocks, we have grid investments, we have power capacity, and we have also net cash flow. So we have an electricity demand taken as an output from the outside. We have the grid tariffs, power capacity, and importantly, we have an investment criteria that we define. This is often very difficult to get from with an equation. So we often have to make a correlation and try to match the model to the final results. So if we simulate this model, we can see here some of these non-linearities that I mentioned before in the break to some of the colleagues. So how the evolution of money could be affected by different decisions, and by how the power capacity that actually is, we are losing power capacity by depreciation. In this case, considered zero, but how the cash flow would be changed when we invest more per year, or when the electricity demand would grow per year. So we could see that net cash flow grows when net income, the net income grows, and then the next cash flow grows. And also this is because the electricity demand that we can represent here. Also, this we see the red part. It's growing also as defined in the loop. So we could see how the evolution of net cash flow, power capacity, which is actually what we have here in the value creation and value capture, is what we are representing here, would change over time. Okay, so this is already a model that has the two stocks, and already, we don't have a significant amount of loops. So we don't have loops that already are connecting the two parts. But if we go to a bit more sophisticated model, when the investments are changing the grid extension and the capacity, so we could see a different element in this loops analysis. This is what Roberto also mentioned before. So we could see this grid extension and investment affecting the power capacity, affecting the load rate, investment criteria, investment per years, investment and grid extension. So these three examples show how to make specific blocks within the model. So that we would like to, we need to play with the data we have, and also that the amount of assumptions that we make. So net cash flow, we could obtain data. Power capacity, we could obtain historical data. And this is what we need to match with the evolution of our model, knowing initial power capacity, knowing initial, in this case, cash flow, and also knowing price per gigawatt, investment per years, and this is what is the investment criteria that could affect by different conditions. So we could, as I mentioned before, we could also include here different conditions. For example, we only invest when the net cash flow is positive, right? So we are not investing when we don't have money in the account, right? So all these conditions represent the model. And from these examples that show very basically how these specific parts could be made, I will just want to show you very quickly how a large scale model looks like. So please, because it has many parts, so let's just have in mind this: customers, assets, and value capture. Okay, and this value proposition of customers is affected by the regulatory framework. So if I show you the value proposition, we could see that we have added different converters and different inputs of the evolution of the number of customers per voltage level that determines the number of customers. And we have defined the different tariffs for the different voltage levels, the different customers, and the regulatory framework, of course. We had to map, we have seen different colors, but I just wanted to show you. So here we have the allowed revenues per voltage level. So we need to know, we need to read the reports. Just don't pay that much attention to the slide right now. So just listen to me. So because here we have allowed revenues per voltage level. This is what we see from the reports of the regulator. We need to read the reports, see what are the mechanisms driving the regulatory allowed revenue per voltage level, per year, and then map what are the different components. These components encompass what are the forecasted electricity distributed, what is the forecasted cost, and so on. And this determines different components of the total allowed revenue, which all of them link to the total yearly allowed revenue. So in this case, this total allowed revenue is reflecting the equations of the regulator and also is reflecting the inputs from the DSO side. What are the inputs from the DSO side? Let's come to the DSO part, which is the value creation part. Okay. Sorry for the jumping, but it's just want to explain to you as easy as possible. And here is the grid assets part. Okay, infrastructure, assets, value creation, capacity. So we have how, for example, this is familiar to you, this power capacity, how this power capacity evolves. We did it for per voltage level, and we add how much the operation and maintenance affects the capacity of the lines, how much these lines are lost because of the depreciation, how this depreciation it's coming from. So it comes from the remaining useful life of the assets that is affected by our new investments and by the loading rates of the assets. This loading rate, of course, that we have here, utilization, comes from the division between the power demand and also the power capacity of the line. So you see how everything starts connect together. So we need to do the exercise that we made before with these specific examples and do this, start to build these specific subsystems within our model. Validate per subsystem, and then start building up to this final equation, final model that we have here. So that's the main idea, because we will have to adapt to the data we have. So we have data on the total allowed revenues, we have data, aggregated data on total investment per voltage level, and this is what we have to validate with the overall model. So at the end, the model is not validated until you have all the subsystem validated. So this is very, very important. So you need to build step by step, start building value creation, the impact of the value proposition, how the regulatory framework works, how all of them connect to the net benefits, and how the digitalization part also it's impacting the other two parts. And for this, we validate with historical data. So I went very fast. I know we cannot cover all the details, but I have everything in the preprint that we are preparing for the model. That if we want more information, you can I will share with you, and we could of course have more specific tutorials on the creation of this data specific model. But let's leave it here, because I don't want to overwhelm you with so much information. Okay, so this hands-on model, as I mentioned before, this is the three exercises that we saw, was the first entry point to understand this large-scale system dynamic model. In this case, we model the business dynamics of the DSO in Portugal, the main DSO in Portugal. So we want to explore how the DSO invests, how the DSO makes benefits, what are the costs, how this is affected by the regulation, and how all the variables link together. And you will see it in a second. First phase of this large-scale model development, as Roberto anticipated the main subsystems, we anticipated that. But I just wanted to show that, of course, the use case is the Portuguese use case. We use the main one that is operating in Portugal continental and serves more than 99% of the customers. And we need to define a validation period. We need to define a period where we have data enough. So we chose from 2012 to 2021. that limits ourselves to that period in terms because we don't have all the digital technologies in that period. We need to represent exactly what this period had. We need to make a replica of the business model for that period. We need to represent the regulatory allowed revenue. We need to represent the evolution of smart meters, for example, in that revenue. And in next studies or in next periods, with that model validated and with new data and with a new set of technology, we could do forecasting and policy analysis. But in this case, with this study, we are focusing on this part, validation and sensitivity analysis of the large scale model. This is what we mainly do in this study. So we wanted, with this large scale model, coming back to one of the first slides, it's how can we switch for the conventional approach on this open loop to a more system-based? System-based, of course, we could also include the DSO interaction, and we could include interaction of other stakeholders. But in this case, we represented some of the main elements. So the DSO part with the part of the grid investment, with the part of digitalization investment, and with an aggregation of all the costs and benefits. We represented the regulatory allowed revenue, so all the incentive mechanisms and all these specific branches that you saw in the model, and how this affects to the customers and the electricity demand coming from the customers, so all the tariffs and so on. So this is all the elements that we have in the model. And don't be scared by the complexity of this slide, that this is more close to the complexity that we have in the Portuguese model. Because what I was showing to you before, let me put the laser. It was the regulatory allowed revenue, how this affected the tariffs. We had the part of the grid assets, the power capacity, how this affects the utilization rates, and how the utilization links to the health of the assets, and how this health of the assets also bring to InnoCyPES, ID, all these quality of supply elements, and how this links to capital expenditures, operational expenditures, and so on. From the digitalization side, we have the technologies that we have in the Portuguese reports. So we read the reports and we saw a smart meter, substation automation, these small dots, maybe you're curious, that represents per voltage level in the terms of the gray, and the blue represents that there are many technologies, so that the substation automation has technologies per voltage level. So this is an aggregated model, aggregated representation of the model, yes. So this digitalization part has influence in the benefits where we could reduce operational maintenance cost from substation automation, from smart meters, from innovative smart grid investments, which is data analytics. Also, we include cybersecurity as a cost, which is because it was in the reports of the DSO. And also automatic customer attention and handling, which is one of the technologies that we also saw and that linked to the reduction in operational maintenance cost. And we linked how this total operational costs and CapEx retrofit into the regulatory framework. So all the model is connected. So the DSO part connects to the regulatory part connects to the customer part, and the customer influence also investment and the loading rates of the assets. So this is the way to integrate such a model. So in the way we found was more appealing also to the view to represent as a white box model. But before that one, so let's focus now on what are the causal links between the grid operation. So let me give an overview of what is inside this orange part, the blue part, the pink part, the green part, okay? So in the grid part, we have all the different investments. We have how this utilization, I don't want to go into deep, but just because this is recorded and so on, if you want to know more on the causal links that we specifically include in the Portuguese model, we take a look at these slides. Also, we have it in the paper and explained, but this is the overall logic. Remaining useful life of assets, affecting new investments, length, affecting also the number of failures, affecting InnoCyPES ID, and we validated also all these specific parameters. We validated InnoCyPES, we validated ID, we validated levels of investments, we validated power capacity evolution. So that's the way to make sure the whole model is validated. You need to validate per system. You need to validate multiple variables. So we could not stop in one specific subsystem. This is on the digitalization part, how the digitalization brings costs in cybersecurity, how the different technologies provide impact on duration of failures. And of course, to invest in digitalization, we consider not only grid utilization and the life of assets as it go down, but also technology maturity and so on. Okay, so these are all the different elements that we consider. Of course, this is doesn't show all the voltage levels, but we did it for low voltage, medium voltage, and high voltage. This is the aggregation of the total benefits. Let's say our back as a company. So we have all the operational costs and all the investment costs coming to the back of the company, and where we aggregate everything that is coming from all the subsystems. And this is the regulatory framework. We detail all the regulatory framework in Portugal, and so how all the components, for example, depreciations in the grid per voltage level, cost of renting some of the infrastructure that is actually part of the municipalities in Portugal includes or affects the total revenue, and how this total revenue is different per voltage level. And here, a key factor is that this total revenue we consider an update factor and a proportional link to the tariffs. It's very important to clarify that the regulatory allowed revenue, is not a single element in itself, but we are talking about what is the impact to customers. So the total revenue, it's going to be paid by the final end customers, right? So that's going to be important for the conclusions. Here for the end users, we have a description of the number of users. We have historical data and also the electricity consumption during all the horizon period from 2012 to 2021. And I would like to show some results on the validation. So we validated different elements. We validated CyPES ID. We can see here the evolution of historical CyPES ID in low voltage, medium voltage for the model, and also the evolution of the model. This is the response of the model to this CyPES ID, for example, ID in this case. This is the evolution of also the model. The gray is the historical allowed revenue. And the pink one is the response of the model. We did the same for voltage levels and in aggregated values. So we found a good compromise in terms of validation. How did we find the compromise? Of course, as our colleagues also from AI and all the disciplines, we need to use metrics. Which metrics? Depends on the application and the field. In this case, we use root mean square percentage error and mean absolute percentage error. Suggested by the literature to represent what is the error of the model. Of course, this error could be arguably higher than in AI models. It's not a 99% accuracy model of error, of course, because we are dealing with socio-techno-economic system where we had to make assumptions and correlations between variables that we don't know. So we found that with a compromise of lower than 5% of root mean square percentage error and lower than 9% of error in other of the variables was enough to represent the influence of the policy. So the model was able to react properly to changes in investments, changes in policies, changes in regulation. So we validated the model with these different metrics. And the third phase, which is, of course, my favorite one, is on the simulation. Once we have the model validated, for the Portuguese case, from 2012 to 2021, what do we do with it? So we want to test policies. We want to test how changes in the model lead to different net benefits or so, in comparison always to the baseline, in comparison to the current scenario in the model. So the reality in the Portuguese case. How these net benefits or from investing in digitalization or conventional investment how much are for the DSOs, for end users, and also for end users, how much is the impact on grid reliability or quality of supply when we invest more in digitalization or we invest more in conventional investments? And how do these results change when we, for example, increase the demand or increase or reduce the reliability, or, for example, may have a better regulatory scheme? No, I know it's a lot of information, but basically we're doing a sensitivity and a scenario analysis to test our model. So in the first sensitivity analysis, and this is actually one of the most important parts of the result. And please, yes, just take some Yeah, it's okay. So that's it's the audience is ready. So if we take from the DSO perspective, and net present value, as I said before, is a metric that summarizes us that the net benefits against the cost over a certain amount of period, right? We simulate from 2012 to 2021, and we have the model validated. What if we change? And we add a proportional element, so we change and we invest 5% more in comparison to the baseline in conventional investments, or up to 15%, or less, or we invest less, we invest 10% less or 15% less than the baseline. Or what if we do the same with digitalization investment? We see here in this sensitivity analysis, because it's relative to the current investment, that with investing more in conventional investment, the DSO would have lower net present value. So the costs are going to be higher, so these costs are not going to be recovered by the tariff that much. So the net present value will go down for the DSO when investing in conventional investment. So it's not something we want to do. I mean, it makes sense, of course, that it's not something that brings benefits. It's something that we have to do to make sure that the reliability and the users have the proper service. However, we will not make profit out of it. So, however, when we see digitalization investments, most of the categories of digitalization investments have not reached the benefits yet. However, lead to lower reduction in net present value. We could say an exception, the case also of smart meters, where we had some data on the number of benefits, and that data was from several reports cited in the literature, but specifically optimistic, so we have to say. But here it was pointing out that more investment in smart meters, maybe due to the fact that in Portugal at that time, from 2012 to 2021, there was not that big investments. We see that it leads to higher benefits, in this case, net benefits. So let's move out of the DSO world. So what happens to the total allowed revenues and what happens to the tariffs of the users when investing more in conventional investment? We invest 15% more, for example, this generalized, that makes it means an investment in all the others at the same time. What if we invest 15% more in all the others at the same time? So we will have an increase in the total allowed revenue proportionally also in the tariff around 0.22%. What happens when we do that percentage investment in digitalization? Well, the investment is also lower, so we will have 0.07% on increase in the tariff. So we see that, and confirms what we were discussing before with Peter Hermans, right? On that digitalization has a lower impact on the final cost for the customer. So that's specifically why we also try to put the focus in these technologies, which have could have a lower costs in terms of rollout, and also lower impact to the end customers. Having said that, not all the investments in the grid are avoidable. We need to acknowledge that some of the grid investments are grid expansion, accommodation of new customers, and that needs to be done. So it's the DSO have the obligation of providing this connection, or also have the obligation of replacing some assets when they are broken, of course. But we are talking also about, in general terms, of all the investment, how this could actually impact the customer. So we need to read in that way, because I can see that there could be a specific question there. If I were in the audience, I would ask, why is this comparing this? Is this a fair comparison? And that's what we wanted to clarify. From the DSO perspective, we could say from also the user's perspective, the electricity not delivered. So how the electricity not delivered is changing by investing more in conventional investment or in digitalization. Well, we saw here by the assumption that we have that only medium voltage, maybe because the medium voltage in Portugal have a lower remaining useful life, more investments there would represent more reduction in electricity not delivered. Okay, so no, actually, I have to correct myself. So because more investment in these technologies, in the high voltage and the low voltage, because have a lower remaining useful life, would have a more impact in the reduction of the electricity not delivered. Okay, but if we take a look in the digital part, the reduction percentage in the electricity not delivered, it has a an order of magnitude of difference. So we see also a big impact in the electricity not delivered when investing a percentage more in digitalization or in conventional investment. So these are the big results that we found for the sensitivity analysis. And what can we say for the scenario analysis? What happens when we change the reliability, the electricity not delivered, the external conditions of our model? Well, we see that the baseline case, no investment more, it's the Portuguese model validated. It's having a specific net present value, but when we invest 20% more in the grid, in different scenarios, let's say baseline, investing more or more pessimistic in terms of reliability or more optimistic in terms of less, more reliability and also lower customer demand, we see that the net present values overall in this more grid investment could go down, in grid investments go up, but as I said, we cannot invest only in digital. We need to invest also with a compromise in the grid, specifically on the extension investments and renovation. So this hybrid investment is showing that also a hybrid combination of these two technologies could be optimal, not only investing in conventional, but we need to consider the digital area in the equation. So that's the main idea. What is the evolution of the tariff? So this confirms the results of the sensitivity analysis also. The total out revenue is affected also by if we invest in the grid, we invest in digital, or we invest in hybrid investments. And the same for the electricity not delivered. So we have consistent results over the scenarios. And this is what we had on the Portuguese model. So, okay, we are good in time. Yeah, perfect. So I would like to give a summary. Thank you very much for following with a lot of attention, because I throw a lot of information to you, a lot of complexity. Let me summarize. So basically, we deal also together with Roberto in the analysis of cost and benefits of digitalization. We address the barriers also of digitalization in the energy sector, of course. And we deal, and you actually from this session, you know the principles of system dynamics, you know how to apply and make a very simplistic model of system dynamics. You are able to expand that to the distribution grid domain and are able to make the causality and the correlation analysis that we have. Of course, you are equipped to also assess and build links that are hidden within the regulatory environment and in the various analysis, and you're able to define policy implications and policy measures that can arise when investing more in digital or not. So thank you very much for following with so much attention, and I would like to encourage you to ask as many questions as possible.